All right, we're back at it. And it seems like the image was kind of off, so I had to fix it a little bit. But now it's good. All right, so I'm going to be doing these questions, and well, hopefully, okay, if you have any questions as you watch, you can ask. I'll be, okay, assertive to your questions. And well, let's get down to this. So this is 2016 Common Exam number 3 for Math 111. And of course, remember, if you have any questions, you can ask me. I'll be looking forward to answer them if I can. All right, so let's see. So we're trying to maximize the area of this rectangle, right? So we have that the horizontal side, okay, of the rectangle is x, and the vertical side is y. So the area, okay, is going to be x times y, and the derivative of the area with respect to x is just the product rule, okay? So it's the derivative of xy. So that's going to be y, right? The derivative of x is 1 times the second, which is y, plus x times the derivative of y. So that's just y prime, or dy over dx. And so dy over dx, we can find it easily, okay, using the first equation that we found for perimeter. And over here, we can simplify this by saying that x plus y equals 5. And so y equals 5 minus x, meaning that dy over dx is just negative 1. Okay, so we can substitute dy over dx into our function for our derivative of the area. So the area is simply, okay, the area dA over dx, the derivative of the area. It's just y, okay, and then minus x. So what happens is, in order to optimize the area, we have to find the critical point, okay? So we have to set this equal to 0. And when we do that, we have that y is equal to x. So when y equals to x, we have a critical point. And well, clearly that will be the maximum. That will be the maximum area. So what happens when y equals x? Well, we have the following. Let me go over here, okay? We have the same rectangle, right? But now y is x, and then x is x. So what's the area? X squared. And that's the maximum area you can get. All right, so that was question 1. Let's go to question 2. All right, so it says, given the equation y equals x squared divided by x squared minus 1, find any intercepts and asymptotes of this function's graph. Then B, find any critical points and determine if it is a relative maximum or minimum using the second derivative test. Sketch the function using the relevant information from parts A through C, okay? So, well, first things first, right? We can find the x and y intercepts over here really easily. So we have y equals to x squared divided by x squared minus 1. We set x equal to 0, right? Let x equals 0, and then we find that y is equal to 0, right? So in that case, that means we have y's and x intercepts, x equals 0 and y equals 0. So, okay, y intercept and then x intercepts at 0, 0, okay? So it's basically right over here in the center. Let's see, are there any asymptotes? Well, definitely there has to be some sort of asymptote. Let's see where the denominator is undefined. Okay, so when the denominator is equal to 0, the function is undefined. So if x squared minus 1 equals 0, then x equals to plus or minus 1. Meaning that we have two asymptotes, vertical asymptotes to be more specific. So vertical asymptotes at x equals plus or minus 1. And as you can see over here, we can already lay out, okay, this vertical asymptotes. I think I'm going to have to make this graph a little bit larger because the function's not going to fit. Okay, let's see if I somehow can manage to make this larger. All right, well, we'll have to do that last. That's just part C. Okay, so we simply have the asymptotes at x equals 1 and negative 1. And we want to, okay, find where the critical points are. But let's see if we can keep looking for more asymptotes. Okay, so if you remember from algebra, since you have a rational function of the same powers on top and bottom, right, the same greatest powers, then the horizontal asymptote is just the ratio of those coefficients, right? So in this case, we have y equals x squared over x squared plus 1. And well, the ratios of the coefficients of the highest powers is just 1 over 1, which is 1. So the horizontal asymptote is at at y equals 1. And you can prove this using calculus, right? You can say that the limit, okay, as x approaches infinity of the function, right, x squared over x squared minus 1, well, that's equal to the limit as x approaches infinity of, we're going to divide by x squared on top and bottom, so we're going to get 1 over 1 minus 1 over x squared. And what happens when x squared approaches infinity? Well, 1 over infinity is 0, and then we have 1 over 1, which is 1. So that just proves the fact that the horizontal asymptote is y equals 1. So we're going to have something like this. Let's see if I can draw this. Okay, so it's something like that. That's one asymptote. Then we have something like this, and then something like that. Okay. So we have 3 asymptotes. 1 x-intercept and one y-intercept. So that's part A. Pretty easy, right? 5 points right there. Okay, now let's do part B. Part B is asking to find, okay, the critical points to determine, and we're going to determine if at those critical points we're going to have either a relative maximum or a relative minimum, okay, using the second derivative test. So we're going to do the, we're going to get to the common approach, which is just taking the first derivative of our function, which will be, okay, y prime equals to, we're going to use the quotient rule here, so the derivative of the top times the bottom, which will be 2x times x squared minus 1, and then minus the derivative of the bottom, which is 2x, times the top, which is x squared. All of that divided by the bottom squared, so x squared minus 1, and then squared. Alright, we can simplify the top. As you can see, this over here is going to get you to 2x cubed, and this is negative 2x cubed, so that cancels out. And then we distribute the 2x into negative 1, so we get negative 2x. All of that divided by x squared minus 1 squared. And in order to find, okay, the critical points, well, we can find where the derivative is, okay, 0 or undefined. Right, but as you can see, it is undefined at x squared minus 1 squared, right? So it's undefined at x equals plus or minus 1, but we already know that they're asymptotes, right? So it's impossible for them to be relative minimum or relative maxima, right? Because they're approaching either negative infinity, positive infinity. Well, we will see. So we're just going to see where it's equal to 0. So when the derivative is equal to 0, we just said that the numerator equal to 0. So negative 2x equals 0, which means that the critical point is, well, at 0. Good. But we want to know if it's either a relative maximum or relative minimum, right? Usually, vertical asymptotes are never crossed by any graph, but horizontal asymptotes can be crossed. So we can't just assume like, oh well, it looks like it's going down, right? Because there is an asymptote like that, and it's not going to cross it. Well, we can't just assume that, right? Because sometimes graphs can cross horizontal asymptotes. So in this case, we have to use the second derivative test either way. So we don't have to bother thinking about that. So let me move down. Let's see. The second derivative test is, well, essentially taking the second derivative of this function. We found the first derivative, so let's take the second derivative. So we're going to get the following. So y double prime is equal to, okay, the derivative of the top again. So we're going to use quotient rule and chain rule. So that's going to be negative 2 times x squared minus 1 squared, and then minus the top, which is negative 2x, and then times the derivative of the bottom, and here we use chain rule. The derivative of the inside is 2x, and then the derivative of the outside is, well, we bring 2 down, so that will be 2 times the original, which is x squared minus 1. So we subtract 1 from the exponent using the chain rule. Now, all of that is divided by the bottom squared again, so x squared minus 1 to the power 4. So we can kind of simplify some things here, but let's see. I mean, all we're looking for is what's going on at 0, right? We're looking for what's happening at x equals 0, the critical point, right? Because we want to see if this is going to be a maximum or a minimum, a relative maximum or a relative minimum. So let's just straight up substitute by 0, right? We don't even bother simplifying this. So y double prime, okay, at x equals 0 is just going to be equal to negative 2 times 0, okay, times negative 1 squared is just negative 2. And then we have 0 times whatever that is, right? This is over here becomes 0. Times all of that, that's just 0. Divided by 0 minus 1 to the 4th, which is 1. And so we get that is negative 2. What happens when the second derivative is negative 2? Well, we say that it's concave down, okay? Concave down. Meaning that if it's concave down at this critical point, then the critical point must be a relative maximum, right? It has to be a maximum because it's concave down, right? So the only critical point where the derivative is equal to 0 has to be right there. And that's the case. So let's see. That's part B, okay, part B. And then let's see what else is on part B. Okay, so we found the critical points. Now sketch the function using the relevant information from parts A through C. Okay, so we already found all of this. Now it's time for us to sketch the graph. Well, that's pretty simple here. We have, okay, we know the asymptotes, we know the critical point, and we know if it's a maximum, right? So now we can actually say that it's going to look like this. So it's going to be, let me change, can I change the color on this? Yeah, there you go. Okay. So it'll be something like this. Goes from negative infinity up to 0 and then comes down back to negative infinity. Okay, and then over here at 1, right, over here we're going to have a positive coming down from infinity and then all the way up to 1. It approaches 1 as it goes to infinity. And the same way like that. Okay, so that will be your function. And I mean, you can kind of prove that this is how it goes by taking some limits, you know, just to make sure that that's the right answer. You can take the limit, okay, you can take the limit as x goes to 1 from the right to see if it's actually infinity of the function, which is x squared divided by x squared minus 1. And so if you think about it, you could take, like, say, you know, 1.1 from the right? So that's 1 from the right. Squared divided by 1.1 squared minus 1. Well, if you keep doing that, right, if you say like, okay, 1.0001, that's just going to give you a, you know, small number divided by a very, very small number. So that's just positive, and it's positive infinity. Now we can take a limit, okay, as x goes to 1 from the left to see if it's actually negative infinity over here, right? Because that is approaching negative infinity. So that's going to be x squared, right, over x squared minus 1. And suppose we're going to take 0.009 squared and then divided by 0.0009 squared and then minus 1. Of course, the 1 is greater than whatever this is, so it will be negative. And a number divided by a big number, which is negative, is, well, negative infinity. Okay, so that's about it. And of course, the limit as x approaches 1 of this function does not exist because clearly the function, the limits, okay, from either side are different. Now let's move on to question 3. Okay, so for question 3, we have for the function f of x equals cosine of x over 3, find the absolute minimum and maximum values on the following range of x values. Okay, so and the range, this is the domain, I would say, is from pi over 2 to 4 pi, right? So we can kind of evaluate already some of the critical points. We know that 2 critical points are going to be the 2 endpoints, right? These 2 endpoints. So let's calculate what's going to be the value of the function at the endpoints. So the value of the function at the endpoints, well, we have to find what's f of pi over 2, right? What's f of pi over 2, and then we also have to find what's f of 4 pi. That's what we know for now. That's what we know, okay, is going to be our endpoints. So let's see if any of these will yield a nice value. So we have cosine of, okay, pi over 2 times 3, which is 6. And that's going to be a half, right? Because pi over 6, if you remember your unit circle, okay, pi over 6 is located somewhere over here. And that's going to be, that's pi over 3. That's pi over 3. Over here is 1 pi over 6. This is 2 pi over 6, which is pi over 3. So the cosine of this will just be the square root of 3 over 2. Okay, so that'll be the cosine over there. Now the cosine of 4 pi over 3, okay, cosine of 4 pi over 3, well, we know that that's just 1 pi over 3 more than 3 pi over 3, right? And 3 pi over 3 is pi, so it's somewhere over here, and then 4 pi over 3 is an extra third, so it's somewhere over here. And that clearly is negative a half, so that's negative 1/2. Okay? So we have that. And let's see. We also want to know what the critical points of this function is. So let's say we're going to take a derivative, so let's take f prime of x. F prime of x, okay, will be the derivative of cosine of x over 3. So we use the chain rule and we get negative 1/3, okay, of sine of x over 3. We set this equal to 0 to find the critical points, and we get that this is equal to, okay, sine x over 3 is equal to 0. And so if we take sine inverse on both sides, we get that x over 3 equals to sine inverse of 0. And now you have to be careful here because, well, we know sine inverse of 0 is just 0, right? But since we have an interval, we have a domain that covers more than just one, okay, cycle, right? One full cycle, one full rotation around the unit circle. So we know that sine inverse of 0 is 0, right? But we also have to consider that it's not even on the interval. So we have to find the critical points in the interval. We have an interval from pi over 2 to 4 pi. Now, sine inverse of pi, right? We have 0. We have sine inverse of pi is 0. And our interval is starting from pi over 2. So that is clearly a one of the critical points, okay? So pi over 2 and pi, right? Because sine inverse of 0 is pi. What else? We have sine inverse of 0 is also equal to 2 pi, equals to 3 pi, and 4 pi, and so on, right? Every pi equals to 0. And it ends here. So that's going to be the last endpoint. All right. So we can say that, therefore, x equals to 3 times all of our, okay, possible critical points. So we have pi, so we have 3x equals 3 pi. We also have 3 times 2 is 6 pi, and so on. But we're only, okay, falling in this interval that we're given, which is from pi over 2 to 4 pi. So 6 pi is irrelevant, and we only care about 3 pi. And pi as well. Yeah, I forgot about, well, pi, not really, because we multiply by 3. There you go. So we have pi over 2, 3 pi, and 4 pi. So those are going to be our critical points. So let's find, okay, what's going to be f of 3 pi. And that's just going to be cosine of 3 pi over 3, which is cosine of pi. and that's -1. Okay, so given that this is our, okay, these are all our endpoints, and we found the values of them, then we can say that this is going to be our absolute minimum, right? So we have an absolute minimum at x equals pi. Okay, so we're looking for the absolute minimum, and that's going to be -1. Okay, so which is at 3 pi pretty much. There you go. So that's your absolute minimum. All right. So let's see. For question 4, question 4 is acute integral. I wish I had those for my calculus 112 common exam, but unfortunately it's not the case. So let's see. That's just the integral, okay, the integral of x squared divided by x minus the square root of x over x dx. And well, x squared over x is just x, so that's going to be the integral of x minus, and the square root of x divided by x, that's x to the 1/2 divided by x to the 1. 1/2 minus 1 is -1/2. Okay, so that's going to be 1 over the square root of x. Or just x to the -1/2. You can do that too, if it confuses you. All right. Now the integral of x is just x squared over 2. And then the integral of 1 over x to the 1/2, right? Or the integral of x to the -1/2, right? Is going to be, okay, we have to add 1 to the exponent. So it's going to be 1/2. And then we divide by 1/2, which is basically multiplying by 2. So we have minus 2 times x to the 1/2, or the square root of x. And don't forget plus c, right? Your arbitrary constant of integration. If you forget c, well, your professors are going to get a heart attack, and you're going to get points off. All right. So let's see. Oh, actually, let me look at the last problem. I just realized that this over here, okay, cosine of pi over 6. Cosine of pi over 6 is greater than, in absolute value, right, is greater than cosine of pi. So that means that shouldn't be, okay, that shouldn't be the absolute maximum or absolute minimum. I was saying that this is the absolute minimum. Yeah, because -1 in absolute value, right, is not going to be less than √3 over 2, because √3 is something that's greater than 1. But, well, let's see. -1, like, it's going to be, what, 1.5 squared, something like that, and then divided by 2. No, it's going to be less than 1 eventually, yeah. So this is right. Just fact checking here. Okay, now let's move on to the next question. All right, so for this one, given the function y equals x cubed plus 6x squared plus 9x, right, find any critical points and determine if it is a relative maximum or minimum using the second derivative test. Find the intervals for which this function is concave up or concave down. Sketch the function using the relevant information from parts A through C. All right, so let's see. Well, first things first, right? Take the derivative. So for part A, we're going to take the derivative. So y prime is just 3x squared, and then plus 12x plus 9. To find the critical points, we set the derivative equal to 0. We factor out a 3. We get x squared plus 4x plus 3 equals to 0. We can factor that quadratic, okay, and that's going to be x plus 3 times x plus 1. So our critical points are at x equals -3 and -1. Boom. So we need to know if these are going to be relative minima or relative maxima. In order to do that, we can, either do a line test, but here they are suggesting the second derivative test. So let's take the second derivative of this function, and that's going to be y double prime equals to 6x, right, plus 12. And then we want to test, okay, each of the critical points at the second derivative function over here. So we want to find what's f double prime of -3. And we also want to find what's f double prime of -1. And that's going to get you to 6 times negative 3, right, plus 12, and negative 1, okay, times 6 plus 12. Now, this is going to give you negative 18 plus 12 is negative 4, and this one's going to give you 6, positive number and negative number, okay? Now, what can we conclude from this second derivative test, right? Well, we can say that at x equals negative 4 over here, this, because it's negative, right? I'm sorry, at x equals negative 3, because the second derivative is negative, we can say that it is concave down, right? Concave down. And when it's positive, well, it's going to be concave up. All right? What happens when something's concave down? Well, we know that if there is a critical point, it's going to be a maximum, right? Relative maximum. And if it's concave up, it's the opposite. It's going to be a relative minimum. So you just write down, okay, then we can say that at x equals 2, at x equals negative 3, you're going to have a relative maximum, okay, relative maximum, right? And at x equals negative 1, okay, at x equals negative 1, you're going to have a relative minimum. That's just part A, okay? So now for part B, we're going to find the intervals for which this function is concave up or concave down. Well, that's pretty easy now that we know what's the second derivative, right? If we know the second derivative, then we know the interval. And let me move down, or we could just do it here. There you go. So we know that the second derivative function, y double prime, is just 6x plus 12. Okay? And so we set this equal to 0 to find where the critical point is, and we get that x equals negative 12 over 6, which is just negative 2. So we can do a line test. We can put negative 2 in the middle, and then we can test values around it. We can test, okay, x equals 0, and we can test, negative 3. So what happens when x equals 0 with the second derivative over here? So 6 times 0 is 0, right? It's going to be positive. So this over here is positive. And what happens if it's less than negative 2? It's going to be negative. So that means that when it's negative, it's concave down, and when it's positive, it's concave up. So we can say that the function is concave down, okay, for the interval of negative infinity to negative 2. And then it's concave up, okay, concave up for negative 2 to negative infinity. To positive infinity. And it's all parentheses, right? Open bracket. Because the value of negative 2 is not included. It wouldn't make sense for it to be both concave up and concave down. So it can't be either of them. All right. So let's see. Now the last part of this question is just to sketch the graph. Okay, sketch the function using the relevant information. So let me zoom in. Let me zoom in into this graph and see what we got. All right, so we found that the zeros, each of them, okay, the zeros are going to be at negative 1, right? So one of the zeros will be at negative 1, and the other one is going to be at negative 3, right over here. Well, that looks like a negative 3, right? But it's actually at 2, so it's right over here. Okay. What else do we know? We know that the critical point, okay, the critical points are going to be at, each of them is going to be, negative 1 and negative 3 are going to be the critical points. The zeros are at negative 3 and 0 itself. Okay? Yeah, because if we go back to our original function, y equals x cubed plus 6x squared plus 9x, right? And we set this equal to 0, then we find that this is x, right? We factor out an x when we have x squared plus 6x plus 9. and that's a perfect square, and that's x times x plus 3 squared. What happens when we have a perfect square? Well, that's basically a multiplicity of 2, meaning that the 0 doesn't cross the x-axis. It just touches it. Okay, it touches the x-axis and bounces off. So we have x equals 0 and x equals negative 3. And a negative 3 is going to be the multiplicity of 2. So it will never cross that axis. And we can also take advantage of the fact that we know that before negative 2, so in the interval from negative infinity to negative 2, it's concave down. So we can already kind of start sketching this, right, from here to here, like that. Because we know it's going to be, okay, multiplicity 2, and it's concave down, so it's got to look like that, okay, somehow. It's close enough. Now, what are the values, okay, of the relative minima and maxima? We know that we have relative minimum at negative 1 and negative 3, right? So, well, we already know what the value of the relative maximum is. It's just going to be 0 right over here, since it's just, okay, at 0. At the value of y equals 0. So, let's see. The other critical point is at negative 1. So we substitute it into our original function. So f of negative 1 is just going to be negative 1 cubed plus 6 times negative 1 squared, and then plus 9 times negative 1. And that's just going to give you negative 1 plus 6 minus 9, which is negative 4. So the value of the relative minimum is going to be over here. And then we can finally finish the sketch. It's going to be something like that. It's going to go back up, cross at x equals 0 and y equals 0, and it just keeps going to infinity. That's going to be the cubic function, okay? And we can use, you can even use Desmos. It would be nice to use Desmos on the exam, but, well, unfortunately, that's not the case. So the function was, right, x to the power of 3. We have plus 6x cubed, okay? And then we have plus 9x. And so we find that, wait, I made a typo, right? Yeah. This is squared, there you go. So that's going to be the function. And we know that the multiplicity of 2 comes here because it just bounces off. And then we have a relative minimum over here. Okay, so that's going to be question 5. Now let's move on to question 6. So for question 6, we're asked to estimate the area under f of x equals sine of x between 0 and pi using the right endpoint of 4 rectangles of equal width. Okay, show the graph of the function and you're approximating rectangles. So we're going to sketch the graph of this function. Sine of x, right? It's a pretty simple graph. So we have an interval of 4 different rectangles. So that means that n equals 4. And we're trying to find our RAM, right? The right endpoint approximation for the Riemann sum. Okay, so if n equals 4, and we know that the initial value, okay, is going to be 0, the initial value of x is 0, and the final is going to be pi, then we can say that delta x, right, the change in x, is going to be the final value b minus the initial value a divided by the number of rectangles we have. All of that's going to be 4 minus 0, which is 4, over, my apologies, it's not 4, b is pi. So that's going to be pi minus 0 divided by 4. So pi over 4 is delta x, meaning that we're going to add delta x starting from 0 up to pi. So 0 plus pi over 4 is, well, pi over 4. Pi over 4, right? And then plus pi over 4, we get pi over 2. Plus pi over 4 is going to be 3 pi over 4. And we can represent this in the unit circle just to remind ourselves of the values of the sine function. Okay, we have 1 pi over 4 is right over here. 2 pi over 4 is, well, pi over 2, which is right over here, right? 3 pi over 4 is here, and pi is here, okay? And remember that the values for the sine function over here is 0, over here is going to be root 2 over 2, over here is 1, and then it comes down in the same manner. Okay, now we have the function starting at 0, it goes up to 1, right? And then it falls down to 0 again. And we're going to use the right endpoints, so it's going to be something like that. That's going to be one rectangle, okay? So this over here is going to be one rectangle, this is going to be the second rectangle. Okay, that's going to be I believe this comes down over here. Yeah, there we go. And then this is going to be the third and the fourth, which is just, well, 0. Okay, so now all we have to do is find our RAM given this information. So our RAM, okay, our RAM is just going to be delta x, right, a change in x, multiplied by the values, each of the values of the right endpoints. So we have f of pi over 4 plus, okay, f of pi over 2 plus f of 3 pi over 4, and then plus f of pi, which is kind of irrelevant since we know it's going to be 0 over here, right? So this is basically, if f is sine of x, then f of pi over 4, okay, and given that delta x is pi over 4, then we have that the RAM, the right endpoint approximation for the Riemann sum is going to be pi, okay, times f of pi over 4, which is right over here, right? It's going to be root 2 over 2 plus pi over 2, which is 1, plus f of 3 pi over 4, which is root 2 over 2 again, and then 0. All right, so we have that, that's going to be, this is pi over 4. We have pi over 4 times 2 times root 2, which is root 2 plus 1. Okay, so that's going to be the value of our RAM for this problem. Okay, so now let's evaluate the indefinite integral. Okay, over here, integral of 2x cubed minus 5x plus 7 squared minus e to the x dx. So this is a pretty nice integral. So let's see, the integral of 2x cubed, well, we add 1 to the exponent, right? That's 4, divide by 4, so that's going to be 2x, okay, to the 4th divided by 4. And then we have minus 5, okay, x squared divided by 2. The integral of 7, okay, squared is going to be plus 49x. And then we have minus e to the x, and then plus c, the constant of integration, which you should not forget. Okay, over here you can simplify, that's going to be 2. X to the 4th over 2 minus 5x squared over 2, and then plus 49x minus e to the x plus c. All right, that was a kind of a break. Okay, let's go to the next question. 8. We're going to find the linear approximation of the function f of x equals ln of 1 plus x, centered at x equals 0. Use this linearization to approximate the value of f of 0.1. Graph both the linearization in the original function on the set of axes below. Now this is basically, okay, the first two terms of the linear approximation of the Taylor series, right? Or the Maclaurin series, to be more specific, because it's centered at x equals 0. But we're not going to talk about that. You will see that next semester. So we know that the linearization, well, would just be y equals to f of, okay, 0, right? Because it's centered at 0, plus f prime of 0 times x minus 0, which is just x. So f of 0, okay, is just going to be ln, okay, of 1 plus 0, which is 0. So ln of 1 goes to 0. And then f prime of 0 is the derivative of f prime of f, right? So that's going to be plus 1 over 1 plus 0. And then multiply by x. So that's going to be y equals x. That's going to be the linearization. Okay, it's not that complicated, right? And so if we want to approximate the value of f, okay, f of 0.1 for this linearization, we substitute 0.1 into our linear function for the approximation, and we get that y equals 0.1. So f of x, f of 0.1 is approximately, okay, 0.1. And that's a pretty good, okay, a pretty good approximation, let me say, because if you actually go to decimals. But let's first try to graph this over here. So let's graph both ln of 1 plus x and the linear function y equals x. Oops. Okay, so we have ln of 1 plus x is basically ln of x shifted 1 to the left. So we're gonna start from negative infinity, okay, over here with an asymptote at -1. It crosses 0, and then it just keeps going to infinity. Now, for the linear function y equals x, which is pretty simple, is basically tangential with ln of x over here. And 0.1 is, well, it's really small, it's somewhere over there, so the values of f of x over here are going to be pretty close to y equals x. All right, so if you want to see, let's we could graph it on decimals. So we have y equals ln of, okay, x plus 1. Actually, I had it already. Yeah, so we had something like this. And then we have y equals x, right? And then if we want to find ln of 1.1, right? If we want to find ln of 0.1, I mean, then we find that it's negative, okay, 2.3, right? But we're trying to approximate at x equals 0.1. So 1 plus 0.1 is 1.1, and that's 0.095. If you round to one decimal place, you get 0.1, which is, essentially what we get from the linearization. All right, so let's move to the next question. This is the last question, question 9. Yeah, evaluate. Oh, this is part of that, I think. No, it says problem 10 and then problem 11. Okay, so it's 11 problems. All right. Now for this question, we're going to evaluate the integral, okay? Once again, very nice integral. Okay, so this one just requires one simple technique that we call U-substitution, or just a substitution, right? You could choose your substitution to be any letter. It doesn't really matter. You could choose it to be A, B, C. Well, C, I don't know about that because, indefinite integrals already have a C, okay, assigned as the arbitrary constant. So let's say it's going to be, I don't know, W. Okay, so W equals to 3x, right? Because we already know what's the integral of cosine x, right? So that's why we are going to do a U-substitution. So we know that dw is 3 dx, meaning that dx equals dw over 3. We can substitute this into our integral, and we get that the integral of cosine 3x is equal to the integral of cosine of w times dx, which is dw over 3. We can bring the 1/3 outside of the integral. The integral of cosine w, the w, is just going to be just sine of w, right? And that comes from this kind of calculus unit circle version. We have cosine over here. We have cosine w here. We have sine w, negative cosine w, and then we have negative sine w. When we want to differentiate, we go clockwise, right? And then when we want to integrate, we go counterclockwise. So therefore, if we want to find the integral of cosine u, okay, I mean cosine w, that's going to, okay, we're going to go counterclockwise once, and we end up on sine w. So that's a nice trick if you want to, okay, you know, just in case you forget your trigonometric integrals or derivatives. And so we get that this is equal to 1/3 sine of w, and w is 3x. And then don't forget your arbitrary constant plus c. Okay. Now for the next problem, we have limits, very nice limits. Okay, so here we have, okay, we have the evaluate the following limits, allowing positive infinity and negative infinity as possible values for a limit. If the limit does not exist, explain why. Show all work, okay, 5 points each. So the limit of e to the x minus 1 divided by x squared as it goes to infinity, as x goes to infinity. Okay, you know, first thing I will do is I would directly substitute x equals 0 into the function. So we get that this is equal to e to the 0 minus 1 divided by 0. And we get that this is going to be 0 over 0, right? It's in indeterminate form. So we can use L'Hopital rule since it's going to be continuous on the open interval, okay, from 0 to infinity. Okay, so if this function is continuous, the top function is continuous, right, for all values of x, and the bottom function is continuous for all values of x, then we can take the derivative of the top and then the derivative of the bottom, and then find the limit of the ratio of each. So we know that the derivative of e to the x minus x, okay, minus 1, so this is basically the limit, okay, using L'Hopital, right, using L'Hopital's rule. This is the limit as x goes to 0 of e to the x, right, the derivative of e to the x is e to the x minus 1, and then the derivative of a constant is 0, divided by, okay, the derivative of x squared, which is 2x, and then we directly substitute again. We get that e to the 0 is 1, 1 minus 1 is 0, and 2 times 0 is 0. We get indeterminate form again. So we have to use L'Hopital once again, okay? So this is basically the limit as x goes to 0 of e to the x over 2. And then we get that that's going to be a half. All right, for problem number 11, you know, just don't like try to substitute immediately. Try to see if, you know, you could kind of simplify the expression. And in this case, that's the case. You know, you can actually simplify it. As you can see, you have x over x squared, so that x cancels out, and you get that this is the limit as x goes to infinity of e to the negative 3x divided by x. Okay, so, and that's going to be 0, okay, 0 over infinity, okay, which is just 0, right, because e to the negative 3x, and then you substitute x by infinity, you're going to get e to the 1 over e to the infinity, which is 0, okay, so 0, and then over infinity, well, that's just 0, right? So that's just going to be 0. Okay, so now let's do part B, and it's B for each problem. Yeah, I think I was supposed to do part A for this and then part B, but that doesn't matter. Okay, so now for this over here, we have the limit as x goes to pi over 2 of 2 tangent of x over secant square of x. Now, if you directly substitute, you're going to get that tangent of pi over 2 is infinity, and secant square of pi over 2 is infinity. So it's infinity over infinity, indeterminate form. Perfect for L'Hopital's rule, right? But the problem with this is that it's too complicated. You know, you don't want to complicate yourself in the exam. So see if you can simplify the expression first. If not, then go ahead and use L'Hopital. But as you can see, we have that this is the limit as x goes to pi over 2 of 2 times tangent of x, which is also sine of x, divided by cosine x. All of that divided by secant square x, which is essentially 1 over cosine squared x. And look at that. 1 over cosine cancels out, and we have, okay, the limit. The cosine goes up, right? This goes up, and then we have the limit as x goes to pi over 2 of 2 sine x, cosine x. And then we can substitute pi over 2 already, and we get that sine of pi over 2 is 1, but cosine of pi over 2 is 0. So the limit is 0. Now let's do the limit of 2x squared times sine of 1 over 4x squared. And then I was thinking about this when I first saw it, and I remember that there exists an approximation for sine of x. Sine of x, right, equals x. For the first, that's going to be the first power, the first term for the Maclaurin series approximation, right? So if you use that fact, you could already find the value of the limit. But I think that would be illegal to do on the exam. This is not right, because it's not a small value of x. We're considering large values of x. In fact, we're considering the values of x as they approach infinity. So that's invalid. But in that case, you still will get the right answer, which is quite interesting. If you were to do that, you get 2x squared times x, which is, in this case, not x, but whatever is inside of sine. So 1 over 4x squared. And you get that the x squared is cancelled out, so that's a half. All right? So just to like keep in mind in there. But don't do this on the exam. It's just out of curiosity, right? But let's do it the right way. So if we substitute infinity, okay, to see what happens, we get infinity, right? Infinity to power of 2 is infinity, and then sine of 1 over infinity is sine of 0, which is 0. So infinity times 0 is indeterminate form. That's going to be an indeterminate form, but it's not the one where you can use L'Hopital's rule. You can use L'Hopital's rule when we have 0 over 0 or infinity over infinity, okay? So you might have to do some rearrangements here. So one thing that is commonly done in order to solve this type of limit using L'Hopital's rule is a algebraic manipulation, right? So what you do is you say that this is essentially the limit as x goes to infinity of 2x squared sine x, sine of 1 over x squared, right? Multiplied by, 1 over 2x squared, and divided by 1 over 2x squared, essentially multiplied by 1, right? And then what happens here is that this cancels out, and we're left with the limit as x goes to infinity of sine of, 1 over 4x squared divided by 1 over 2x squared. So that could be one way, but we have to see if it works. So if we substitute infinity, we have sine of 1 over infinity, that will be 0. And then over here we have 1 over infinity, and that's 0 over 0. So that's good. That means that L'Hopital's rule can now be used because this is in L'Hopital indeterminate form. So we can take the derivative of the top and bottom, and then we get that this is the same as the limit as x approaches infinity of the derivative of sine of 1 over 4x squared. So we have to use the chain rule. The derivative of 1 over 4x squared, so it's going to be negative 2, right? Because it's going to be, this is going to be the same as, 1 over 4 times x to the negative 2. And if you take the derivative, you get negative 2, right, over 4, and then x to the negative 3, using the chain rule, right? Well, not really, it's just the power rule, but we just manipulated it algebraically. So this is basically negative 1 over 2 x cubed, and then times the derivative of the outside. So the derivative of sine, remember it's cosine, cosine of 1 over 4x squared. And then we're going to divide by the derivative of 1 over 2x squared, which will just be, the same as this, right? But then the 2 cancels out. So we have negative 1 over x cubed. the negative 1 over x cubed cancels out, and cosine of 1 over 4x squared as x approaches infinity is cosine of 0. Cosine of 0 is 1, so that's going to be 1/2, right? That's going to be the value of the limit using L'Hopital's rule. If you use a Maclaurin series approximation with k equals 1, right, then you're going to get the same, but that's not valid, okay? So don't use that. All right, so I think that's it for today, for the Math 111 Common Exam review. I hope you found this video interesting and useful, right? And well, I wish you the best of luck. All right, so I'll see you next time. Thanks for watching.